So yeah, speaking about the compilers and about the interpreters here, compilers is one particular part which is actually used to compile the code, right? So there might be a number of questions. What is the use of a compiler, and why do we need any of the compilers which a particular user has to work on it, right? So speaking about the compiler here, program needs to be checked by one or the other machines so that it can be used when it comes to the working or checking with respect to the syntax. It can be checking out the semantics or how exactly is the code valid, right, according to the syntax or not. So when do we get to know that the particular code is actually working or not, or according to the syntax, right? So whenever we compile it, once we compile the code, then we get a target program, which is not exactly the output of the program, but still it is much more forwarded towards the next particular working phase. So so translator is anything that converts the high level language program to the low level language. So that's what is all about. We need to make sure that the machine should also understand what exactly you're actually giving it, so that a machine should also understand to work out with it, right? Ultimately, it's all about the hardware, where our fundamental codes and reside, right? So the hardware needs to understand the compile, whatever the compiled stuff, whatever the program, whatever the source program which you actually needed to give, that will be as a target program. So as you can see here in our state here, so source program is actually giving the inputs towards the compiler, and the compiler is giving us the target program, right? So few intermediate things which we need to learn here is we have interpreter. Interpreter is not the same as a compiler. It has few things and few differences from the compiler. So as you can see here, we get, when we send the source program to the compiler checks for relative syntax and how it is working, and we give it towards the target program, and the target program is much more further processed in order to get the output. So interpreter, apart from the source program which it takes, it also takes the inputs, right? So straight away the interpreter, as it already has a source program as well as the input which is fed into the interpreter, we get the output, right? So but compiler, they are much more slower. Why? Because the source program needs to be sent towards the compiler, and the compiler will send you or give you the target program, and this target program should be converted towards, in other words, the obj or the dot class file when you see, or when you take with respect to the Java, right? So those particular programs, we need to give the inputs to those object code, or it can be a class code. They get the input, and we shall work out with respect to the output. So here, speaking about the language preprocessor system, this is how exactly we go, right? So the source program is where the program starts its working, or what exactly we as a humans give, right? We write some code, right? So that's something called as a source code, and this particular source code is sent towards the preprocessor, right? So we all know what exactly a preprocessor is. Before processing, what are the considerations which we need to do, which we need to use, right? For example, you might have seen in your Lex and Yak programs where we work on with respect to the preprocessor, where we add additional information to the existing code or towards the existing source code, where we add few more files to it, so that somehow we can get our output, right? So from the preprocessor, we get the modified source program. That means a few more things which you have added. For example, you have some including files or .header files which you can call, which will be added for the preprocessor, and then it creates one particular bundle of codes, and so that the compactable can be achieved, and it will be sent for the compiler for further use, right? A compiler here utilizes or it checks for the syntaxes and much more things. We have actually 7 different types of phases which are going through the compilers. We shall go through all the 7 phases, what exactly it happens in our particular chapter here, and we'll also understand how a target program is actually generated, right? So now, as you people have already studied with respect to the assemblers, where in the chapter of system software, assembler 1, the generation of object code, the stuff which you have already studied, right? So compiler comes before assemblers, right? So where compiler checks for the syntax and checks whether the codes are proper, and this code needs to be sent for the assembler, so that assembler will generate an environment saying that it generates all the opcodes, object codes. It also generates the object program. Once it's done with the object program, your assembler task is now done, right? Next comes your loader and the linker part. Linker and the loader, the object program which you have been generated needs to be brought in front, where you get the particular program into your main memory, that is RAM, and from the RAM you need to bring it, right? That particular work here is something called as a loader, right? Loader takes care of loading the particular program from its memory towards the main memory, right? That's the important task. So once the program loads, now whenever it was loading, it will be in a basis of chunks, and it will be here and there. So we need some mechanism in order to make sure that everything will be linked together. That's what the part of the linker which take care of it, right? Whenever you're linking, and which you need to be providing towards the hardware, linker takes care of utilizing the library files, relocatable object files. It considers the complete thing, and it sends towards the target machine code. That's what the preprocessor system, as in the diagram which you can see over there. So moving on towards what are the different types of compiler which we have. We have a hybrid compiler. Hybrid compiler is where it's a combination of interpreter, or it can be one or more compilers which can be combined together, right? As you can see in the diagram, there are source program which will be sent towards the translator, and translator will actually generate the bytecodes. It gives you the intermediate program or intermediate program, and with the intermediate program we generate, or we give the input, so that this intermediate program with the input will be given to the virtual machine, and the virtual machine will give you the output, right? You also have heard about jitter, right? Just in time compiler in Java. So those are the hybrid compilers. Moving on with the next topic, we have something called as the structure of a compiler. Structure of a compiler is actually a 7-phase, where you can see here in the particular note here, where I have lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, machine independent code optimizer, and code generator, and machine dependent code optimizer, right? So these particular 7 phases have been divided into 2 particular ends, right? So the lexical analyzer, syntax analyzer, semantic analyzer, as well as the intermediate code generator, everything comes in the front end pass, right? And the rest, machine independent code optimizer, and machine dependent code optimizer, they come under the backend pass, right? So one more thing which you need to understand here is, we already know about what exactly a symbol table is. A symbol table is where all the newly encountered symbol will be pushed towards one particular place, where apart from the label name we also give something called as an address. So both of the particular value or the symbol and its value will be pushed towards one particular place, which is called as a symbol table. We also have an error table, which we'll try to understand when we come towards the 4th module of transformation, or when it comes towards the LL of 1, or predictive parsing, right? So every particular phase here, symbol table is automatically accessed at any given point of time, right? Lexical analyzer can see the symbol table. Similarly, syntax, throughout all the phases, every other phases can actually see the symbol table, right? One more thing which you need to understand here is, we have, or we give a stream of inputs, as with our maybe with respect to a standard input. Let's assume here the standard input which I am considering is my keyboard, right? So all the character string, or the number of keys or alphabets or numbers, whatever the characters which you are sending, will be collected from the lexical analyzer, and the lexical analyzer work of lexical analyzer is to accept all the characters which it encounters. It checks according to whether the inputs which you are sending is according to the syntax or not, right? So once it checks syntax here, in the sense it looks for the regular expression, right? It considers or looks into the regular expression, is my code according to the format of regular expression, whatever which you are looking for. Once if I get to know that it is in the form of a regular expression, then it identifies those character stream into meaningful characters, something called as a token. These tokens are further processed or given to the syntax analyzer so that it generates the syntax tree, or you call it as a parse tree. So these particular semantic syntax analyzer will give us the parse tree, and the parse tree will be utilized to generate the intermediate code. And this code is actually not exactly the complete code which we are looking for. This will be roughly human understandable to the machine understandable code. And once I have this particular code which has been generated, this will be an intermediate code, and it needs to be further much more synthesized, right? So here machine, the independent code optimizer will optimize the code into a much more intermediate representation. Here you can see in the intermediate code generator as well as with the machine independent code generator, it is taking it's giving out the intermediate represent itself. Why? Because in the intermediate code generator it will not be much more which will be utilizable, right? So that means it has more number of steps, right? So the output which we get from the machine independent code optimizer is actually the code which will be much more optimized. Say if I have a 10 lines of code in my output which is given by the intermediate code generator, but the end of the machine independent code optimizer, which will be like a 3 or 4 lines. We shall go through that particular example in the next particular slide here. So before that, once we get the intermediate representation of the code, we send it towards the code generator, right? This is where whatever the intermediate code which we have will be converted into a target machine code. A target machine code is where, as you already seen, when it comes to the system software, we have LDX some value, right? So load into accumulator some value from some register. It can be from R1 and R2, right? So those are called as a target machine code. So these machine code needs to be much more optimized. It will be sent towards the last particular phase of a compiler, which is called as a machine dependent code optimizer, will give you the target machine code. This is all about the 7 different phases of a compiler, which you can see. One is with the lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, code generator, and machine dependent code optimizer. That is what the code which you actually will be looking for or will be worked out, right? So here the question is, I said that first whatever the code which you write as a source program needs to be the stream of inputs, which was the input for my lexical analysis. So here the target machine code is what I got as an output from the particular compiler here as an output. This target machine code which I get from the compiler needs to be pushed towards an assembler, right? So here, as with the syllabus of VTU, it is actually contradictory, where we studied about the assemblers in the beginning, then we study about the compilers. First, the process how it goes is first the compiler will do its job, next followed by the assembler is what does its job. Anyhow, so as I said, the 7 given parts is actually the phases of a compiler is divided into 2 main parts. One is with the analysis part and the other one is the synthesis part. The first 4 sections which you actually saw, they come under the analysis, and the rest 3 will come under the synthesis part. That's what about the front end of a compiler and the back end of a compiler, which we actually differentiate, right? So regarding the generation of the syntax tree, it comes under the analysis part. Once you generate with respect to the output or the target code, it comes under the synthesis part, right? So we shall take a small example here, how exactly the phases of a compiler which works out or which repeats. This is a very important question in the examination point of view. Why? Because in their examination, where the particular question might be in this way. right? Explain the different phases of compiler. With an example, work out with the way how a particular target program has been generated, right? So we shall see with respect to the 7 phases how individually they work out with each particular phase, and we shall take one example with this, and so that concludes the 7 phases here. So the phase here is the lexical analysis, which is actually used for a scanning. As I said, I have n number of inputs which are coming through, and these inputs will be sent towards the lexical analysis. And once I get the input from the input stream towards the lexical analysis, so meaningful output needs to be generated. That's something called as a token, right? So here one way of calling the token is also a lexeme, right? On reading the character stream of source program, it groups them into meaningful sequence. Groups them is where the regular expression comes into picture. So meaningful sequence is called as lexeme. For each lexeme, analyzer produces as output a token of a form, right? So this will be the particular token, how exactly it looks. A token will have a token name and its attribute value. So token name will be abstract symbol used in the parser. So we have a key which will be given for each individual token, and it has its own value beside it, right? So these particular name and with the value which will be pushed into the symbol table, so that at every given phase the particular symbol and its value will be referred throughout. Syntax analysis is the second way, which we call it as a parsing, right? So parser uses these token whatever has been generated, the output of the scanner, and it creates a tree-like intermediate representation that gives us the grammatical structure of the token stream. Whatever the inputs which we have given, we have to give some meaningful way of using it. The meaningful way is where we created a structure out of it, right? A structure in the sense tree. Here we call the tree as a parse tree. Looking into a small example here, for grammar e tends to e plus e or e star e or num, we have an input something called as a 2 plus 3 star 5, right? So we have one as a grammar and one as an input. By making use of this grammar, construct the particular parse tree in order to get an input of 2 plus 3 star 5, right? So as my work here is, there's a rule of where I need to work out with the starting production. My start production here is e tends to e plus e, so it's mandatory for me to use that particular production, right? So e is tending to e plus e, so I have 2 plus 3 is what I'm looking for. So 2 plus 3 into 5, so which is a feasible production which we can use plus. So first I start with e plus e, where e is a number, right? So here 2 plus the other side I have another e, but I'm not giving it as a num or a value 3. Instead of that, my input symbol is actually 3 star. So is there any production giving me that particular structure of 3 star? Yes, that is e tends to e plus e production. So that value of e will be utilized by 3 star 5. Ultimately it is e star e, then that e will be replaced by a number which is 3. So this is how syntax analysis will happen and the parsing tree will be generated. So the third phase is semantic analysis, uses syntax tree and information in simple table to check the source program for semantic consistency with language definition. So here the major things, what happens here is it gathers the type of information. Type checking will happen, looking for whether it is a valid operand and which is used, and so it also check for some type conversion also, right? So language specification may permit some type of conversion, right? So next phase is intermediate code generation. So ICG is the short form which we use it. The intermediate code during the processing may be in the form of a syntax tree or reduced form of source code. So in the fourth phase we speak about the source code, unless until the fourth phase is here, the fourth phase, which is intermediate code generator. It's all about getting the stream of input. One way of parse tree generation, the second way of parse tree generation. From parse tree, in the fourth phase we get the intermediate code, which is not the straight away the code or just the translated code which you can call. So property here is should be easy to produce, should be easy to translate into the target machine code. That's the use of intermediate code generation. The code optimization is where machine independent way of working comes into picture. To improve the intermediate code or to get better target code, better in terms of faster or shorter or less power consuming code, and instead of using int to float operation, replace integer by its floating point value directly. We shall work out with respect to the example which I have it in my next particular slides here. So code generation, input from the input intermediate representation maps into the target language. If target language is a machine code, of course it's a machine code, the instructions are translated into sequence of machine instruction to perform some task. So judicious assignment of register to hold variables is actually used here. The last way is, okay, so what are the tools which are used in order to work out with respect to the construction of a compiler? One, we need a parser generator. The task of parser generator is automatically produce syntax analyzers from a grammatic description of a program language. So scanner generator scanning the inputs, that means lexical analysis which is happening here. Syntax directed translation taking care of the parse tree towards the intermediate code generation. So code generator generations work out with respect to getting out the target code. Data flow analysis engines facilitates gathering of data and how values are transmitted from one part of program to every other part. So compiler construction toolkits provides the integrated set of routines for constructing various compiler phases. So these are the 6 particular tools which are integrated in all the compiler, right? Speaking about a compiler here, we also have a compiler in order to check all the codes whether it's working fine or not, right? A small example here is you all have already studied about Java compiler. That is, if you had run in your command prompt, there is something called as a javac, right? So javac is which speaks about the Java compiler. So these compilers should be equipped with all these tools, right? So they go under one application after the another application, right? So that's where compiler is used for, and giving us where exactly what wrong is apart from the syntax, right? Where exactly you lost track when it comes to the syntax, right? So application of the compiler technology is implementation of high-level programming languages using the modern object-oriented programming concepts like data abstraction and inheritance properties. So optimization for computer architecture where parallelism is involved at instruction level, multiple operation executed together, and at preprocessor level different threads run separately. So when it comes to the memory hierarchy, building up very large and fast storage, right? So these are the advantages. So designing new computer architecture, we have reduced instruction set computers and specialized architecture with the data flow machine, vector machine, and much more machines, right? So when it comes to the program translation, binary translation increases the software availability. Hardware synthesis happen when it comes to Verilog. VHDL reduces the time and effort. Database query interpreter, the compiler is used with respect to the SQL query, effective retrieval, compiled simulation, reduced redundancy in code, and the next one is with the software productivity tools where we use it for type checking. One particular type may not be working fine with respect to the other type, right? So bounded checking, right, with respect to the buffer overflow, the security issues, optimize range check, and error detection tools, memory management tools with respect to garbage collection, where there might be cases that there are some unused memory blocks by the objects, and these objects which has been created needs to be deleted. And deletion in the sense I need to clear off memory. So automatic memory management tracks all memory related errors and with respect to the leaks. So differences, if you go with the compiler interpreter, Compiler translates the entire program in one go. Interpreter converts high level language into intermediate code, and it goes one line after the other line, right? So interpreter is line by line execution. Compiler is one particular time the entire program itself will be run, right? So here the condition is there are some issues with respect to which is fast and which is not, right? So therefore the as according to this particular definition, or in my first particular point, compiler is much more faster than that of interpreter, right? So the error reporting is with the line consuming displayed after entire. Basically, error reporting is one time consuming when it comes to the compiler, because the compiled code needs to be looked, right? Even though it is faster, error detection is slower, right? So when it comes to the interpreter here, errors are displayed after one after the other. That means each line gives us each error if in case there are any errors. So as in each line we get to know the error, so the error will be displayed much more earlier, right? So conditional control statements are executed faster. Conditional control statements are executed slower when it comes to the interpreter. When it comes to the memory management, memory require is more, right? When it comes to the compilers, memory requirement is less when it comes to the interpreter. So program need to be compiled every time, and every time higher level program is converted into the lower level program. Difficult to use when it is in the compilers, easy to use for the beginners in the interpreters. Translate one and then run the result, like run once, use many. So here read, check, execute, everything is used, so slower, right? Used for not standalone systems. Example here is C, C++ for the compiler. Example for interpreter is Python and Prolog. So that's how the mechanism which it goes. Source program to the compiler. Compiler gives the target program. We give input to the target program. We generate the output. But thing is much more simpler when it comes to the interpreter. Source program with the input, we push it towards the interpreter, we have the output which is ready, right? So I just gave you the 10 different points, or the differentiation between the interpreter and the compiler here, which you might expect in your examination. Also, this is about the example program which I was actually explaining you about. You might get one program or one example making use of a given particular source code generated as with respect to the target code, right? Source program to the target program. So as I said, once I get the stream of inputs, things will be pushed towards a number of phases, and the phases will be with respect to the 7 phases, and ultimately in the end I get my values. So I suggest you, I have one, I'll show you with respect to one example here. You can run with respect to other programs looking towards it, and it's pretty simple. First thing is you have the question as position, which is equal to initial plus rate into 60. So when you give this information towards the lexical analyzer, first thing lexical analysis which it does, it strips off each given stream into each division of inputs. So as you can see here, position has been identified as identifier 1 equal to initial has been identified as identifier 2 comma, that's the second identifier, plus, so rate has been given as identifier comma 3. So 60 is actually a value which has been given as a same. So here we generate a syntax tree where a syntax analysis is getting the inputs, and the syntax analysis is giving us a way of a tree-like structure. And as you can see here, the tree-like structure is with respect to the inputs or the values, and the next particular phase will give me my complete working of the case, right? So once I have with the identifiers here, so I generate my whatever you call here with respect to this table is actually called as a symbol table, right? So here the identifiers what we have is the position, initial and rate, position, initial and rate respectively. I have the 3 values, and identifier 1 equal to, that means identifier I have 1, Towards the left hand side of my equal to, I have identifier 1. Towards the right hand side, I have plus. Towards the left hand side of the plus, I have identifier 2. Similarly, towards the other side of my plus, I have identifier 3. So that's what the identifier comma 2, and I have a star. Towards the left side of the star, I have identifier comma 3. Towards the right hand side, I have a particular value, say 60. So this complete term here, what you see is actually the syntax tree, right? So this syntax tree is not actually much more simple, right? So some more analysis needs to happen with the semantic, and then we try to understand the another syntax tree, which you can see here in the phase. So in this semantic analysis, we have only change. What happens is, if there are any numbers, right, we identify what type of number it is, right, and we push it in one place or a memory where it can be further used, which you can see in the particular slide here. Once I have the syntax tree which is ready, the next particular phase is I need to generate an intermediate code, which is an intermediate code. So intermediate code generation is a pretty simple task here. I have first identify how many operations you have overall, right? So here first I need to work out with the 60 value which I have. That 60 is an integer, maybe is converting into the float somewhere. Seeing to that it is as a float, it can be integer or a float, no issue with that. So this takes my first code. What are you telling? T1 is a particular variable, right? The first task which you can call the task 1 is equal to into float of 60. That means the value of 60 I am working out with respect to converting into a float, which is 60. The second task is, what do you do with this 60? This 60 needs to be multiplied with identifier, right? So ID3 needs to be multiplied with T1. That's what the second code is. So the third plus here is ID2 should be added with my T2. Getting? So T3 is equals to ID2 plus T2. So similarly, identifier 1 is equal to the ultimate T3. Whatever the calculations which you do with the T3 will be put towards the identifier 1, right? So this is not the complete code. It needs to be optimized, converted into much more simpler task. I need to wave off. I have 4 statements here. I need to convert it into few, right? So as you can see in the next code optimization technique, so I have very few instructions. Previously I had 4 instructions. Now I am converting into 2 instructions, right? So this code optimization is happening. That means I had 4 instructions. Now I am narrowing it down to 2 now, right? So which are the 2? What are the things which I can eliminate? That's the question. So T1 equal to into float of 60. Straight away 60 is what the value. You convert it and push it into the next particular use, right? So I convert this complete statement into just 60 and I use it. The 60 needs to be multiplied with identifier 3, which I cannot much more simplify. Why? Because I need to do the multiplication, then I need to add it, right? Because of a board mass rule, first I have to multiply and then I have to add, right? So I straight away utilize the star or the multiplication value here, ID3 into 60, and I save it in T1. So that's one particular code. The second one is, what can I do? Assigning. Adding and assigning towards the next particular value is what I can do in single line, right? So as you can see here, T1 and T2, which are 2 particular statements, I narrow it down to 1, and the next 2 particular statements I narrow it down to another 1. So this is where optimization comes into picture. I'll tell you why we need to work out with the code optimization is, if I use n number of lines of code becomes bulky. The other way is I'm also stressing out my variables. I'm killing time, right? So once you optimize with the code will be very light. Very light refers to light memory or less memory, and when it working mechanism, it is much more faster, right? So having simple and clean is what the coding is about, right? So once you have the optimized code, you need to send it towards the code generation. Code generation will give you the generated code which can be understood by your particular hardware, right? So here first I have first line of code is T1 equal to ID3 into 60. So what is the operation which I am doing here? ID3 should be multiplied by 60. So that means that I have a floating point variable that is 60 dot over here. So you need to use the identifier 3 value which you need to get it towards the register. So how exactly are you getting the value towards the register? Wrote into a particular floating point R1 comma identifier 3. Identifier 3 is a memory location. From the memory location get it towards the register 1. So then load it into the particular floating point register, right? That's what memory to the floating point register. Whenever you get the value, that's what the load into floating point register R1 comma ID3 specifies. Next thing is I need to multiply this particular ID3 with 60, right? So 60 is the immediate value, as we all know, right? That's why the symbol has a hash before it. So as my value is now with respect to the floating point, I am using a floating point register. Mul_f is where multiplied with respect to the floating registers. So what exactly the operation is happening in mul_f R1 comma immediate value 60 is multiply the value whatever you see with 60 with R1 and save it in R1 itself. Getting R1 previously had identifier 3. The identifier 3 has been multiplied with the 60 value, which is a floating point, and you are saving it in R1 itself, right? So similarly, now what happened? The first term is happened, right? So T1 is equals to ID3 into 60. So what exactly is T1 here? Is identifier 3 into 60, and it is saved in the value. So the first two operations here is already done. So my T1 result is equivalent to R1 result, what it is holding. So once my first value is done, second particular statement here says that T1 value I need to add it with identifier 2. So identifier 2, whatever I had, according to the statement here, the initial plus rate into 60, right? So the initial will be in identifier 2, the value. This I am actually loading into a particular register, say R2, right? So that is LDF refers to load into floating point register R2 comma ID2. That means ID2 is in memory location, get it into the R2 register. And the next statement is add F R2 comma R1. In the sense R1 and R2 add the value, store the result in R2 itself. Next statement is once you have R2, the last I need to assign it to identifier 1. So as simple as that, store from the register R2, push it to ID1. From register to memory operation is what is happening in this particular statement, right? So this is another example. You people can make a note of it. So a index equal to 4 plus 2 plus index, and this is a program which you can sort it out yourself. So a complete method is already there, and yes. So moving on with respect to the next cases here, environment and states. Environment have names and it has locations, and it has some values here. Environment is mapped into names to location in the store. State is mapped from location in store to their values, right? So dynamic mapping exception is where static binding to the name to the location is what happens, where which is speaking about the global variable declaration and location to store once for all. Next we have something called as a static binding. Kindly go through the values here. And so speaking about the structure of a static scope and the block scope, the variables are actually belonging to few blocks at a given time, right? You know about the differences between the local variable and the global variable, right? So that's all about the things here, where the value of, let's take considering this as an example, I have 4 blocks B1, B2, B3 and B4. The use of B4 or the variable which I have there is int b equal to 4 is only with the scope of B4 block, right? That B4 is not outside B equal to 4 value, the B value is not outside, it's not coming outside, right? So similarly the scope of variable a equal to 3 is only within the block 3. Similarly, b equal to 2 is within the block 2, right? So this is about the scope, and I hope if you can differentiate between the global variables and the local variables, this is a very simple topic which you can actually understand quite simple and easily, right? So next case is, I have given a small example here, and next is another example. No issues, you can go through it. Okay, these are the example. I'd like to skip it because this is of not much use. So the next case is about the parameter passing mechanism. You have seen about the parameter passing. There are two types, right? Call by value and call by reference. And call by value is where a duplicate value will be sent towards the called function, towards the calling function, where once the control is done with respect to the calling function, so the control will come back to the called function where the previous value will be there, right? It means the changes, any changes which are done for the variables in the call by value is temporary. So in call by references, any changes made towards the variable is permanent, right? I hope you people already know about this, so we shall just skip it. Next important name is with the aliasing. So aliasing in the sense I give another name for my variable here, right? So alias in the sense the variable can also be called in another name, right? So the consequence of call by reference parameter passing with reference to objects are passed by value. It is possible that two formal parameters refer to the same location. Such variables are aliased to one another, right? So though they may be distinct formal parameters, they may be alias of one another. So let A be array of procedure B. So here P of x comma y it is calling. So I go with Q. So x and A are actually alias, right? So x of I equal to y of I. That's actually called as an aliasing. So that's about the chapter 1. We also have chapter 2 with respect to the second case here, which we exclusively speak with respect to the lexical analysis. So a lexical analysis is where few of the Alexa and the parser, how exactly it speaks, right? This is my first phase of my compiler where lexical analysis work out with the thing. So as you can see here, my source program which I am sending towards the lexical analyzer. This lexical analyzer accepts the source program. It generates the stream of inputs, and meaningful inputs is called as a token, and the token is what actually is required by the parser, right? So every time lexical analyzer will look into the regular expression, sends the token towards the parser, and parser asks the particular lexical analyzer, do we have much more tokens? Every time next token generation is what the input which a parser will be sending towards the lexical analyzer. And from the parser, of course, as I said, symbol table is referred throughout the phases, right? So I have a symbol table. Both lexical analyzer make an entry towards the symbol table, and it can be, if there are any changes which is happening in the parser, that will be making the changes towards the symbol table. So this is a simple phase here with the lexical analysis. Once the parser works out with the case, that means it is further more ready to generate the parse tree, right? So the generation of parse tree is where will be the next particular phase, which will be pushed to the semantic analysis, right? So the task of Lexer is identify the lexeme, stripping out the comments. If we have the comments, what exactly you do within your program, you need to actually neglect it, right? You need to ignore the particular cases, right? You need to neglect the particular values, right? So here, apart from the comments, you also need to be taking off the cases. Like there might be a case of blank, right? There can be cases of a new line character. There can be cases of null. a tab space, right? These things you have to actually ignore it, right? So something called as removing the white space, right? So next thing is task of Lexer is correlating error message generated by the compiler. So keeping track of the line numbers to show the errors. If source program uses microprocessor, the expansion of macros is also done by the scanner. Scanner in the sense the Lexer. So Lexer is cascade of two process, scanning as well as the lexical analysis part. So scan the inputs, and once you get the inputs, that needs to be worked out properly. So scanning consists of a simple processors that do not require tokenization of inputs, such as deletion of commands, the removal of the white spaces or the characters into one. So lexical analysis proper in more complex portion where scanner produces sequence of tokens as output also. So if we speak about the Lexer and parser here, which you already know about as we discussed with respect to the Lexer and Yak here. So Lexer is like getting only the inputs, right? These inputs which a Lexer has will be thrown towards the parser where he can work out with it, right? So a Lexer and the parser is where the tokens jump from here and there, right? Tokens jump from the Lexer and the parser, and the parser asks for the next as according to the figure which we actually saw. Simplicity of compiler design is an important consideration. How simple you design your compiler, how effectively it gives you, right? Compiler efficiency will be improved. Use specialized technique for lexical analysis, which is actually a concept of input buffering. So compiler portability is also enhanced, right? So speaking about the terms of definition of what I mean by token, pattern, and lexeme. Token is actually a pair, consists of token name and an optional attribute value. Token name can be of abstract symbol representation, a kind of lexical unit. It can be of a keyword, it can also be of an identifier. The token names are the input symbols that parameter will be actually processing, right? So what I mean by a pattern? Pattern is the input, right? So the input, whatever we get it, right? Description of a form that lexemes of token may take, right? So what do we know with respect to the pattern? Pattern will be with respect to what you need to match, right? That means a regular expression which comes here can be called as a pattern, right? A token name is an identifier. Pattern is underscore A to Z with the caps A to Z plus. So what does plus refers to? Plus is where one or more occurrences of a given character. So star is 0 or more occurrences of a given the expression or a given character it can be. So lexeme is a sequence of character in source program that matches the pattern of a token, and it is identified by the Lexer as an instance of that particular token. So token name can be a keyword. So here pattern if is actually a keyword. So in order to obtain that as a particular pattern, you need to get a particular character I, and the next character after I should be F, right? So I and F will be my input, and getting this meaningful input is the lexeme, right? So we shall see about what are the tokens and how it looks. If is actually a character I and F, right? So lexeme should be of if. So else, 4 characters E, L, S, E. So else is a simple or a sample lexeme. Comparison operators, less than, greater than, less than, equal to, greater than, equal to, assignment operator, not equal to, right? So less than, equal to, or not equal to can be called as a lexeme. Identifier is letter followed by letter and digits according to the rule, right? So here pi and score can be with respect to the case of identifier. Next case is number, numeric constants, 3.14, 0 and 6.9 exponent power 8, and we have a literal value enclosed within the constant or core dumped. So these are the examples for the token. The another case is whenever there is an error, which happens usually, there can be error in the sense that where I might be having another value which I can be used. So let's take a look about what are the errors and how can we recover from these errors. One is with respect to the panic mode recovery, and panic mode recovery in the sense I have some of the values which are left out. That means I might have deleted it, right? So looking into it, deletive successive characters from remaining input until Lexer finds a well-known token at beginning of input left out. That means a panic mode is in the space of ELSC. I have forgotten E, so LSE is actually given out, right? A compiler need not be panic about LSE because it gives you a number of errors, because LSE is not a valid keyword, or it might not be declared in the beginning, right? So it's not a meaningful identifier, and the identifier is not declared. These are a number of errors which can be found out. Instead of that, if I have else, when you use else will be used with an if statement. If you have a if statement, then followed by LSE, suggests the particular user, or you try to recover itself. The compiler should try to recover itself, so that if I had a particular character else or E for the LSC, it becomes a valid identifier, right? So second thing is the second recovery option is delete one character from remaining input. If, for example, taking an example of ELSE, I can have used double ELSE. That's also one particular of way where error can be generated or error has been created. So deleting one E makes sense for the keyword, right? Or the second or the third condition here is insert one missing character into the remaining character, where I have LSE, so adding E to it will make me ELSE. So that's another way, right? So fourth one is replace a character by other character. Maybe in case of else, they can be ELSA, right? So here a character E has been replaced with A, so it needs to try to say that, okay, instead of E there is Elsa, so replace that A with respect to E again, so that it makes sense, right? The next one is about the transpose into two adjacent characters, where something it can be exchanged, right? Characters might be exchanged, right? It can exchange. For example, there might be a condition called as FI, right? Instead of if, it is FI, right? Everything is the same, but the character has been jumbled. That's about the case here. Next is about input buffering. Input buffering has two types, single buffer and two buffer technique. So what exactly happens in the case is, I have a lexical analysis, I have some inputs which will be actually sent from my lexical analyzer towards the next particular phase. We need some memory in order to save my inputs, right? So what happens, or traditionally the system is, I might be having one case where my input are actually slow, considering or working with respect to the inputs, right? So if my inputs which I am getting, if it is slow, my processor working on this input will also become slow. We need to avoid that. So in order to avoid that, the topic of or the concept of buffering came into picture. That means whenever I have slow input output devices, we need a special type of memory where I can store the incoming characters or processed characters into that memory, called as buffering. If I use one buffer, then that is called as a single buffer. If I use two buffers, then I call it as a two buffer, right? So single buffer is where I start getting the inputs, my characters will be filled one after the other. Once I fill the characters, let's say I have 10 spaces, or considering this example here, I have 4 spaces here, WORL, actually I have a 5 bytes, so each character takes 1 byte. Each character in ASCII is 8 bits, right? So 8 bit is 1 byte, so I have 5 bytes of characters here. So but I have only buffer of 4 bytes. What should I do? So first input character is W, I gave it. Next O, R, L, end with the buffer. The buffer capacity is now done. Buffer is full. So where to put the D? Unless until the working of W has been done, you cannot allot the space for D. So once W has been taken care of, then only D can come and sit over there. Alright. The next case is, one condition is, we use only one single buffer to store the process character from large number of characters from source program. Main override is that lexeme size should always be greater than the buffer size, or else it's of no use. Buffer is 4 here, lexeme is 5 bytes. Fine, working perfectly fine. So if my lexeme is say 1 byte, that means I have only W to be stored. And the buffer is having 4 bytes, only W will come and sit. The rest 3 byte space is wasted. Okay? So the next condition is it reloads the data, removing the old data. Once the working or use of W is done, it is now taken off and it is free for a particular character to use it. So the D will come and sit here. So we should have a pointer to point out it, right? So one pointer will be now actually specifying to which particular input character am I speaking about, right? So we have a pointer here. I think the thing is missing out here. So in the next particular case, we have a much more detailed explanation. So in 2 buffer technique, working with respect to 2 things, with Sentinel and without Sentinel, we'll try to understand what with Sentinel refers to. So we use 2 buffers that are alternatively reloaded. That means once the filling is actually working out with 1 buffer, the second buffer will be empty. Once the full strength of first buffer is done, next I move filling up the second buffer. So alternatively I'll be using the buffers here. We use 2 buffers that are alternatively reloaded. Each buffer has size n, right? So n equal to size of disk block. Usually 4096 will be the byte size. Using the read system call, n characters can be read. So here I have the complete space. The memory has been divided into half. One is used as the size. Here in this case, you can tell that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the size of the buffer. Each buffer here. I have 2 buffers, so 20. So every time I should have a pointer which will be pointing out where exactly I am looking on in the particular buffer which I am using, right? So you need pointers where I started and another pointer to be moving further. That's why you see a begin pointer and a forward pointer for my buffer. Once I done with respect to this particular character, I move on to the next, right? So ultimately I have moved my pointer towards the right hand side. So this lexeme begin says that from here to here is what I need to consider. Alright. So next we have something called as a special character EOF. EOF stands for end of file. It's actually a particular value, EOF 454F46. This value will be not read by a particular as a content of a given file. It just specifies that okay, now it is done with respect to the usage of the whatever the input which you are looking in the file. No more inputs are there. That means we have encountered towards the end of a file. So that's a special purpose character EOF which we use for the case. So 2 pointer maintained. Okay, we have 2 pointers, lexeme begin and forward. Lexeme begin marks the beginning of current lexeme whose extent we are attempting to determine. Forward is scans ahead until a pattern matches is found. When forward reaches end of next lexeme, right? So 2 pointer we retract 1 position back and to return the token. So forward is having to. We need 2 checks in 2 buffer without sentinels. So what exactly is sentinel? Using sentinel, character at the end which is a special character that is not part of the source program, which will be a usual EOF, right? So EOF can be there or cannot be there. That's about the Sentinel. Here in the case, I don't have any Sentinel. This is without Sentinel. I don't have end of file, right? To specify the buffer itself that it is an end, right? So, but here in this case with Sentinel, that means I have a EOF. Okay. Right. Then here check if reached end of buffer or not. Look ahead in at most one character, make previous character as return valid token. So similarly, you have a particular code here. Kindly go through it. It's in the particular book which I have explained previously. Alphabets. Okay, speaking about what are the types here. What do you mean by alphabet? Alphabet is a finite set of symbols. For example, 0 and 1 are alphabets. So string, using the finite sequence of symbols or alphabets, you get the string. For example, 0101 is a string. Language is countable set of strings over the summation, right? So prefix of a string refers to string obtained by removing 0 or more symbols from end of the string, right? For example, BAN, banana. Let's taking an example of banana. BAN is actually a prefix, and banana itself is a prefix of banana, right? And epsilon. Epsilon is nothing but a null character. For all strings, epsilon are the prefixes, right? For all given string, epsilon are the prefixes, epsilon are also the suffixes by default. So suffixes of a string is string obtained by removing 0 or more symbols from beginning of the string, right? Nana and banana itself are the suffix of banana. For example, ban is a prefix, ana is a suffix of banana, right? So substring in the sense string obtained by deleting any prefix and any suffix from the string is called as a substring, right? Epsilon also are substring of banana. Proper prefix in the sense here prefixes which is not epsilon are equal to the string. Now epsilon and the string itself, we cannot use it. Apart from that, we call it as a proper prefix. For example, ban and banan are the proper prefix of banana. Similarly, proper suffix anana and na are the proper suffix of the string. Proper substring in the sense the same string as well as the epsilon should not be used. So example, anan, banan, anana, right? Those are the substring. So subsequence, here is the catch. Subsequence in the sense string formed by deleting 0 or more, not necessarily consecutive portions of string. So here in the middle n is missing, right? Even though if you call that, then it is a substring. Ban with BAAN is a substring of banana. ANAA is again a substring of banana, right? So these important terms you should be good at. So next is operations on the languages. So operation of languages in the sense we work out with respect to n operations. One can be union, concatenation, clean closure, positive closure, right? So here union in the sense I have a set. So I have two set. One is with respect to L and the other set is with respect to M. Using both the values L and M, right? I consider the elements present in L. I also consider the elements present in M. Union of it is called as union of L and M. Concatenation in the sense where I use both L and M, where it can be that first comes the L and whatever the sets which I have in M, both we are utilizing it. So that's called as concatenation terms here. So clean closure in the sense that's a star value here where it can be used 0 or n number of times. That's why you see that. So L star equal to, for a language L star is equals to where my terms can be from I equal to 0 to infinity. So L can be repeated from 0 to infinity. Similarly, positive closure of L refers to L plus, which is like I can repeat the statement I equal to 1 till infinity, where I is starting from 1 to infinity. If it is in clean closure, I am starting it from 0. That means epsilon should also be included in L star. So next is about the regular definitions. For some alphabet set epsilon, for some alphabet set here with respect to the summation sequence of regular definition, D1 is giving R1, D2 is giving R2. Similarly, one definition is giving you sequence of regular definitions, right? So D1 to R1, D2 to R2, similarly Dn to Rn. Each Di is a new symbol not in the particular language and other definitions, right? So anyhow, we will be looking into many such productions there. You will be easily understanding. So Ri is a regular expression with respect to summation of have a language D1 D2 del Di minus 1, right? So how do we identify with respect to identifier here? C identifiers are, what is the rule for an identifier? Identifier should start from an alphabet followed by, it can be an alphabet or a number, apart from underscore, no other special characters can be used. So letters are caps A to Z, small case A to Z, and underscore. Digits are 0 to 9. ID is actually letter followed by letter or digit star, and here letter or digit can have 0 or n occurrences. So similarly, unsigned numbers goes on in this way. We already sorted out with the C identifier, unsigned and signed. So give a look about it. Next is about the algebraic clause for regular expression. This is R or S equal to S or R, where R is commutative. Similarly, here in the next case, R or S or T is R or S, or T is an associative. R of ST is equals to RS of T is concatenation. R of S or T and RS or RS, this is actually a distributive law. And epsilon R equal to R epsilon is equals to R. That means epsilon is identity for concatenation. R star equal to R or epsilon whole star. Epsilon is guaranteed in a closure. R star star is equals to R star. That means star is idempotent, right? If you have a number of stars, it's equivalent to the same star. That's what the example states. Next is the topic related to recognition of tokens. This is a very important statement which you usually see whenever you're working with the grammar. Statement is tending to if expression then statement, or if expression then statement, else another statement, or epsilon. So how to write this particular statement is where in this particular case has been given. So number is tending to 0 to 9 as it is an identifier 0 to 9 plus, and I have a decimal point dot 0 to 9. In the case, this number production is giving you a regular expression where it is unsigned number, decimal number, right, or floating point number. Identifier, this is a regular expression for it. If is actually a keyword, so straight away it will be repeated as a lexeme here. So then else. Relational operator can be less than or greater than or less than equal to or greater than equal to or assignment or not equal to. Alright. So white space, in the sense white space can be blank or a tab or a new line. One or more occurrences can be called as a white space. So next is about the transition diagram. This is how the transition diagram looks like for the case where we saw less than equal to with less than equal to, and less than with other it gives you a retract, return only the less than symbol. Less than with greater than is not equal to, then if I don't give anything, then return equal to, then if it in case that it is greater than, one thing is greater than equal to, or the other thing is just greater than, right? So this is also one important questions which can be asked in your main exam. So write a flow diagram for relational operator is one of the questions which they can ask you, right? So similarly, this is a program working on it. So we have an identifier, letter is tending to, so this is a small example of it. I think you already have given a particular look on this particular example before with the case numbers. Similarly, this is with respect to the unsigned numbers, how a flow diagram or a transition diagram looks like for a keyword of if, or, then, or, else. This is how it looks. Delimiter, white space. These are the example problems which you can actually look into. So by this we have come towards the end of module 3, which we have given a pretty good look into. So these are the assignment questions which I have specified. You can go through it and look into the cases. Alright, then we'll stop at this particular point, and we shall continue in the next class. Alright, so if you have any questions or any comments here, kindly